In this video, I will discuss the LU decomposition method and how it can be used to solve several linear systems with the same matrix A in an efficient manner. So let's take a look at these two linear systems that we wish to solve. So here we have the matrix A times the unknown vector x is equal to this right-hand side with entries 6, 9, and 2 versus the same matrix A but with a different right-hand side vector. Now, how would we go about solving these systems with Gaussian elimination or with Gauss-Jordan elimination? Well, we would perform row operations on this matrix A. And it's important to note here that converting A into triangular or diagonal form for both right-hand sides requires exactly the same operations on A. So if there's a way that we can store these operations, this would give us a recipe for easily solving a linear system Ax is equal to b for a given A for all possible b. So we wouldn't have to redo all these operations on A in order to get it into triangular form, but we could just replay those operations only on the vector b, such that we have a form which is amenable to, for instance, solution by back substitution. Now, this can be done by the LU decomposition. And the LU decomposition looks as follows. We actually convert our matrix A, which is a dense matrix, so in general all entries of A are non-zero, into the product of two matrices, an L matrix, which is lower triangular, and a U matrix, which is upper triangular. And note that these are not unique, so you can actually come up with multiple LNU for a matrix A. So once computed, once we have this decomposition of A into LNU, this allows us to convert a hard system to solve into two easy linear systems to solve. So the original hard system Ax is b, well, we can simply rewrite this as Lu times x is b, since A is equal to Lu. And if we then make this kind of substitution in notation, so U times x, that's an upper triangular matrix times x, that's simply a vector, and we call that y, then we can find x by first solving this intermediate system Ly is equal to b for y, followed by solving ux is equal to y. And it will become clear why this is easier in the next slide. Because if we look at our initial system, this hard to solve system with a dense matrix A, so to solve this is hard because it requires Gaussian elimination of the matrix A. Whereas this system Ly with L, a lower triangular matrix, well, that can easily be solved by forward substitution. So we already have here that y1 is equal to b1, and the rest is simply done by substituting the value for y1 into the second equation, and then the values for y1 and y2 into the third equation. So this will give us the vector y1, y2, y3, which can then be used as a right-hand side into this upper triangular system. So we have this upper triangular system which can be solved through back substitution. So once we have computed L and U, this shows us how we can split the operation of solving Ax is b for x into two sequential systems which are much easier to solve. So a lower triangular system followed by an upper triangular system. Now the hard part is actually to compute L and U. And I will show you that they actually naturally show up when you perform Gaussian elimination. So in Gaussian elimination, what we actually want to do is convert this matrix A into an upper triangular matrix U. So it's already an upper triangular matrix that we are working towards. So we know how to construct U already. And we've seen this in the previous videos on how to do this. Well, we just first start with the first column, try to get rid of this coefficient here by subtracting from row 2, row 1, multiplied with the ratio of this element with the pivot coefficients. And we also do the same for row 3. So this gives us zeros in the first column below the diagonal element. And we do the same thing for the second column, where we subtract from the third row over here the second row multiplied with the ratio of this coefficient with the pivot coefficient in the second column. So this gives us already the upper triangular matrix U. So remember that what we're actually trying to do is we're trying to write the matrix A as the product of a lower triangular matrix with the upper triangular matrix U that we have already identified using Gaussian elimination. Now, how will we do this? Well, we want to find the matrix L, which, when multiplied with U, gives us back A. And we can do this using the operations that we enacted on A in order to convert this to U. And if we can reverse those operations, well, that will give us an indication as to how L should look. So what operations we have to do on U to come back to A. So let's revert these operations, and we see that in order to go from this bottom row matrix to this third matrix over here, what we actually do is, well, we take our operation that we used during the forward elimination and just invert it. So we just see what we have to do to get row 3 prime back. And that is just adding row 2 prime multiplied with this ratio of coefficients to the third row over here. And the same holds for these other conversions in order to go back to our full dense matrix A. Now, this operation over here can be written as a matrix product times the matrix U. So a matrix multiplied on the left side with U. And we can do that exactly in this way. So what does this say? Well, this matrix says that the first row of U should remain untouched. So there is 1, 0, 0 in this row. The second row of U should also remain untouched with 0, 1, 0. But the third row of U, well, the product of these two matrices will have as a third row 0 times the first row of U plus this coefficient times the second row of U plus the third row of U. And you can actually see that this is exactly this reverse operation that we wanted to do over here. So this matrix corresponds to this elementary row operation. And we can keep going up in these sequential operations in order to go back to our full and dense matrix U. So let's take a look what happens if we do this. So in order to go from this matrix, which is equal to this product over here, onto this matrix, well, what did we do? We added to the third row the first row times this coefficient. So that corresponds to, well, I just copied this guy over here. That corresponds to multiplying on the left with this matrix. And we see that in the third row of this matrix product, the third row of this matrix will be the first row of this matrix plus the third row of this matrix, where the first row is multiplied with this coefficient over here. And finally, we do this one more time, and we see that, well, in order to add to the second row the first row multiplied with this ratio of coefficients, well, then we just have to multiply that on the left with this matrix over here. So now we have actually found three matrices which, when one after another multiplied on the left with U, will give us A. And if we actually compute the product of these three individual matrices, we see that this is a lower triangular matrix, and this is equal to our L matrix, such that we have A is equal to L times U. And this gives us kind of a algorithm how to find L and u. Let's look at an example of how to do this. And again, we use our trusted linear system, which we already introduced in the beginning of this video lecture. And the matrix A for this system can be written as such. So this is the coefficient matrix, which we then want to decompose into a lower and upper triangular matrix. So we know that our lower triangular matrix, well, it will have zeros above the diagonal. It will have ones on the diagonal by definition. And we still have to look for the coefficients that we have to put on the lower triangular side, so below the main diagonal. Also, to find u, we need to do forward elimination. So let's get to it. So first we start with the first column, and we want to get rid of this 2 over here. So what we do is, well, we say that row 2 should be, the new row 2 should be defined as the old row 2 minus 2 times the first row. And note that this operation is key to reconstructing our matrix L, because L will hold the inverse operations that we need to do in order to convert u back to A. So in order to convert u back to A, well, what would we have to do is to take this term on the right here, so this guy, and move it to the other side of the equation. Now what would happen then is this minus 2 would turn into a plus 2. So the coefficient that we have to write here is 2 in our matrix L. Next up, we want to get rid of this one over here. And how do we do this? Well, simply by subtracting from row 3 the first row. And again, in order to find the corresponding coefficient on this spot of the L matrix, we have to check how to recover from this forward elimination operation, and it is by moving this term to the other side, and then this minus r1 turns into a plus r1, so the coefficient that we have to add over here is a plus 1. And finally, we need to get rid of this minus 2 term over here. And how we do that? Well, we add to the third row, we add twice the second row, which will give us the matrix U. So this is the upper triangular matrix U. And to get the final coefficient needed to complete our matrix L, we take this term, we move it to the left-hand side to see what would be necessary to recover our original row R3 prime. And this is a minus 2, which then gets added to the L matrix. Okay, so we have identified U and L. Now let's try to solve a linear system. So we have L and U. We want to solve a system AX is B, which can be then rewritten into LU times X is B. And we already mentioned that this can easily be done in 2 steps, by first solving this auxiliary system Ly is equal to B for Y, which is then used as a right-hand side for this second system Ux is Y, which can then be solved for X. So let's give it a go. We first construct this system Ly is B, where L is this matrix over here, B is the right-hand side of the linear system, and Y is a vector of unknowns. Now this can easily be solved with forward substitution, as this is a lower triangular system. So what we find is Y1 is equal to 6, Y2 is equal to 9 minus 2 Y1 is 9 minus 12 is minus 3, and Y3 is equal to 2 plus 2y1 minus y plus 2y2, sorry, minus y1 is equal to 2 minus 6 is minus 4 minus 6 is minus 10. So we found that this auxiliary variable y is equal to 6 minus 3 minus 10. And we use this then as a right-hand side in order to solve our second system, ux is y, which we solve through back substitution, because this is an upper triangular system. So we start at the bottom, x3 is minus 10 divided by minus 2, minus 5 is 2. x2 will be equal to 3, and x1 will be equal to 1. And again, we get the same solution as we did using the other methods of x1 is 1, x2 is 3, and x3 is 2. Now, the advantage of the LU decomposition is that once we have ln u, that the majority of the work actually is done. So it's quite hard to find ln u, but now we can quite easily solve this system to get we can easily solve the system for a different right-hand side. So let's say that instead of the previous value for b, we now have a different value where b1 is 2, b2 is 2, and b3 is 1. So the only thing that changes in our approach is that we have a different right-hand side here in this first system, which we can still easily solve for y1, y2, and y3. And then we can plug this solution for y1, y2, and y3 into this second system over here, this upper triangular system, which can be easily solved using back substitution. So x3 is minus 5 divided by minus 5. x2 is minus 2 plus 3x3 is 1. And for x1, well, we have 2 minus x2 minus x3 is equal to 0. So with relative ease, we were able to solve this system for a different right-hand side. And that's kind of the power of LU decomposition. Now, let's say that we have computed the LNU matrix for a given matrix A from the previous example. And we want to do the same using MATLAB. Well, we see here that we have different matrices. So the L matrix is different and the U matrix is different. And also an additional output of MATLAB's LU method is a permutation matrix. Now, why this permutation matrix is because MATLAB performs pivoting by default when computing LU decompositions in order to decrease the risk of rounding errors. And the only thing that you need to take into account then is when you have this original system AX is B, MATLAB automatically will pivot, so it will multiply with a permutation matrix on both sides of the equation. Here in this case, multiplying with this permutation matrix, and you can check this by yourself, but it basically comes down to switching rows 1 and 2. And then MATLAB will do a LU decomposition, not of A, but of P times A, and you can solve this system in the same manner as you would originally, but the right-hand side should be multiplied with this permutation matrix. That's kind of a side note that you always have to keep in mind when you're using MATLAB explicitly to perform an explicit LU decomposition, that MATLAB does this pivoting by default. Wrapping up on the LU decomposition, the whole idea is to replace this single hard system to solve, AX is B, with two sequential easy triangular systems. With the first, a lower triangular system that can easily be solved through forward substitution, and an upper triangular system that can be solved through back substitution. Also importantly, L and U depend only on A, not on B, and L and U are also not unique for a given A. However, the fact that it doesn't depend on B means that we can reuse it to solve the linear system for different values of B very easily. And the only difference that it makes is that we use a different B when solving this first lower triangular system, which will give you a different Y that is also input to the upper triangular system. Recall that MATLAB by default does pivoting in the LU decomposition. So if you solve this using an explicit LU decomposition in MATLAB, recall that if you use the LU function of MATLAB, that you take into account this permutation matrix such that you have to possibly switch some rows in the B vector, but the rest is completely analogous to an unpivoted LU decomposition. And solving these triangular systems is really easy, so forward or backward substitution. But the hard part is actually computing the matrices L and U, for which we still have to do a Gaussian elimination step.